Good morning, everyone. I am S. Vijayalakshmi, working as an assistant professor at SNS College of Technology. Now we are going to discuss about tag-based register allocation in code generation. Now we are moving deeper into code generation, focusing how compilers use tag-based register allocation to improve efficiency. We have already seen how tags help in code optimization. Now we will see how they are directly impact register allocation or usage at one of the most critical resources in machine code generation. Then last, our objective of that today is simply and so focused as how a DAG represent expressions and learn how to allocate the registers efficiently, and third, to see how tag relationships and help us to optimize code generation by avoiding redundant computations. So let us take a real example. A game developer writing the physics engine, they notice that repeated expressions like a plus b and then a plus b or x into y appearing many times in their equations. The compiler must detect these expressions and then repetitions and reuses previously computed values instead of recalculating them. So recomputing a plus b, this is where tag helps, recalculating them only. Then problem statement is, so our problem statement is, how can we represent expressions that we can detect some common sub expressions and assign the registers efficiently. Remember that registers are limited. Reusing them smartly is the key to performance. Exactly. Then there are more possible approaches. Navy registers allocation. It's a simplest but full of redundant computations. Then going to next allocation is the static allocation. It's predictable but inefficient for complex expressions. Then going to tag based allocation. It's a best approach. It removes the redundancy but requires analysis of expression graph. So we choose tag based allocation because it helps us to share computations and minimize the register usage. So that is the content. The building the tag means it's a directed acyclic graph. Leaves are represents operands, and then internal nodes are represents operators, and then edges show the dependencies between the computations. Then and going to the sub expressions, we move that, for example, a plus b, int a plus b, the sub expression a plus b appears twice, but tag represent it once. It's saving the computations. So building the tag means, let us how the compiler build the direct acyclic graph as parse the expression, check if the sub expressions is already exists in the tag, and then reusing, if yes means reusing that node, otherwise create a new node. Unique sub expressions means fewer registers needed. Shared node means coded also reused. So register allocation using tag means, suppose we once we have the tag means we allocate the registers based on how many times the node is used. Example, N1 node is A plus B. Register assigned as R1, usage count is 2. N2 means A plus B into C is stored in R2. Usage count is 1. So R1 is reused bar A plus B. That means avoids the recomputations. So since A plus B is used twice, we compute it once and store it in R1, reusing it later. This avoids and saves the both time and space. For example, let us apply this in the real example. T1 equal to A plus B, T2 equal to A plus B, T3 equal to T into C. That means tag optimization. Here A plus B is shows that two times, but it's a single node. Register R1 hold the A plus B reused in both. So the code generation is move R1 comma A, add R1 comma B, move R2 comma C, multiple R2 comma R1. This is the code generation in assembly code. And registers used here is 2 instead of 3. Computations reduced, one addition is removed. So code becomes shorter and faster. One addition also removed here. So this is the reuse and optimize computations. Then group activity, it's the same quick activity. Optimize this code using the tag means T1 A into B, T2 A into B, T3 equal to T1 plus C. Think which computation can be reused. Yes, A into B is repeated. So compute it once and store it in a single register. Assign registers to each node means it's used in a single registers. So it's a optimization of tag. Then summarize tags represents the computation efficiently, and also register allocation is guided by node reuse. The compiler minimize the redundant work and save the resources. Then going to this quick evaluation, would the tag still help if all computation were unique? The answer is no, but it doesn't hurt. It still ensures correct dependency order. That is the power of tag-based register allocation. It's the backbone of the optimized machine code generation. How compilers match the tag patterns with machine instructions. So review the tag example before our next session. Thank you.